Okay, so welcome to this section on our expanding universe. So this story begins with Edwin Hubble. He was an astronomer in the early part of the 20th century, and he worked at the Mount Wilson Observatory, which is down in Southern California, essentially right up above Pasadena. And with this telescope, he made a discovery that was probably one of the greatest discoveries of the 20th century. So let's explain what he saw. So here's his telescope. And there's his eyeball looking through it. With this telescope, he peered out into the heavens, and what he noticed, well, first of all, was that there are a lot of galaxies out there. So I'm going to try to draw some of these galaxies. So these are nice spiral galaxies. And so not only did he recognize and see all these different galaxies, but what he noticed is that they all tended to be kind of reddish. Okay, and so by this I mean literally they all had a reddish hue. And based on this observation that they all looked kind of reddish, this is what led to kind of this big discovery. But before we can go fully into that, we have to understand something about how waves travel through space. And the simplest way to start thinking about this is to use the example of sound waves. So imagine it's the weekend and you're really into NASCAR racing. And so you go to your local track. So this is the NASCAR track seen from above. And this is you in the stands. And here's one car coming towards you. And then there's another car moving away from you. Now you notice as the cars move towards you, their sound is high pitched. And as the cars move away from you, that sound becomes low pitched. And this is something that we've all noticed with cars when they move towards us and away from us, they sound different. So you can imagine as the car's moving towards you, it's going like as it moves away from you. So the pitch of the sound actually changes. And this is known as the Doppler effect. So let's take the example of a car that's not moving. And here's the exhaust pipe, the engine is running, so there's the exhaust coming out of it, but the car's not moving, and you're standing right here. The sound of the engine is transmitted via sound waves. So here are the sound waves. And these sound waves reach your ear, and that's how you hear the car. Now, let's start moving this car. So the car starts moving towards you. Trust me, this is the same car, even though it looks different. There's the exhaust pipe, and now here's the exhaust going out this way because the car's moving towards you. Here You are right here. Now what happens is the speed of the car gets added to the speed of the sound waves, and what that does is that compresses the sound waves. So notice how these waves look much more compressed than the ones above. And by compressed, I mean, look at the distance between the peaks, and you can see that in this lower example, when the car is moving towards you, the distance between the peaks decreases. Because this is sound, this has the effect of increasing the pitch of the sound. And same thing if, well, in a kind of the similar idea, if the car is moving away from you, these sound waves get stretched out, and that leads to a decrease in the pitch. So the main takeaway here is that you can tell from the sound, from the pitch of the sound, whether this car is moving towards you or away from you. Now the same thing happens with light. Light, of course, is also a wave. So we can talk about sound waves and also light waves. And same thing, if you were to look at this car in a very kind of sensitive, with a very kind of sensitive detector, you would notice that the car moving towards you looks kind of bluish because the light waves are getting compressed. And when you compress light waves, they turn kind of blue. And as the car is moving away from you, it becomes reddish. And that's because red light waves are more stretched out. So you can think of this as a Doppler effect, but for light waves. Now, of course, at the speed that cars can travel, we don't see this. It has to, for this effect to be visible to our eye, it has to be, the velocities have to be much faster. Okay, but it's the same idea. So if we go back to Hubble's observations, and we try to explain why all these galaxies look red when you look at them. Just draw one more here. The inescapable conclusion is that these galaxies are all moving away from planet Earth. Now, there's two ways that we can interpret that. So these are all galaxies moving away from planet Earth. Now, we can interpret that two ways. We can just, kind of the first hypothesis is that the Earth is at the center of the universe and everything is moving away from the Earth. Or the other hypothesis is that just the entire galaxy is expanding. And so when you think about it, obviously that makes more sense. There's no reason to think that the Earth is at the center of the galaxy and everything's moving away from it. It's a much more reasonable hypothesis that the universe is expanding. And so here's the planet Earth, kind of a little blue dot. And so from our perspective, oh, I don't know what happened to the blue dot there. There we go. So from our perspective, everything is kind of red shifted. So that's what that's called. And it looks like everything is moving away from us. But if we were to occupy any of these other galaxies, everything would look redshifted as well. So everything is moving away from everything else. So wherever you go in the universe, it's going to look like everything is moving away from you. And again, that's because it's the entire universe that's expanding. And so this was an absolutely astounding conclusion. And whoops, sorry. And it's astounding because before that time, everybody thought that we lived in a static universe. And by static universe, I mean it was thought that the way the universe looks now is exactly the way the universe looked billions and billions of years ago. And if you were to go into the future, billions and billions of years from now, the universe would look exactly the same. And so this idea of the static universe, this is what people thought before Hubble's experiments or observations in the 1930s. And even really smart people like Albert Einstein believed in this idea of the static universe. Now, the other ramification for this observation that the universe is expanding. So again, you can just think of these as galaxies scattered about. If everything is expanding, so again, this is just from the vantage point of, say, planet Earth. Then what this means is that you can essentially play this tape backwards and reverse the direction. You can reverse this expansion, essentially, reverse the direction of all these celestial bodies. And what you find, so if we reverse the direction, what we find is that all the matter in the universe was once at one location. So all the matter in the universe was once at one location, and then something happened, a big explosion, which I'm sure most of you are familiar with. This big explosion is known as the Big Bang. And the Big Bang blew apart this this massive matter at the center of the universe, and created the universe that we see now. And so this all happened. This Big Bang happened 38 billion, not 38, 13.8 billion years ago. And so ever since then, the universe has just been expanding. All these celestial bodies have just been moving away from each other. And this was such an amazing discovery by Edwin Hubble that, of course, he's been memorialized by the Hubble telescope, which is up here, which orbits planet Earth and has just this amazing view on the galaxy, or on the universe, because of it's above the atmosphere, and so it has very clear views. And so it's brought, oops, it's given us, the Hubble telescope has given us amazing pictures like we see down here in the lower right. This is called the Star Nursery, and what we're looking at here is essentially stars being born from all this essentially cosmic gas and dust. So that's just an iconic picture that's been produced by the Hubble telescope. Now, this story doesn't end there. Because if we, again, go back to the Big Bang, where we had this central, essentially mass accumulation of matter that just exploded. So this is that explosion. It was thought that after the Big Bang, so just to make this clear, so this is the Big Bang. It was thought that at some point, all this matter that was ejected out would start coming back towards the middle. And you can imagine why this is. So here you are. Imagine you throw a rock up in the air. Here's that rock. Well, you know what's gonna happen is that rock is gonna come down, and of course it's gonna come down because of gravity. So here's that. You throw the rock up the air, and it comes down because of gravity and lands on your head. And so it was thought that the same thing would have happened after the Big Bang, that at some point galaxies, these celestial bodies, would slow down, just like this rock slows down. And at some point, because of gravity, everything would come back together. Again, so you can imagine throwing this rock down and it's being pulled down by gravity. Same thing, gravity would pull all these celestial bodies together in an event called the Big Crunch. And so gravity was assumed to be the key player here in slowing down the Big Bang and bringing about the Big Crunch. Now, what people have discovered since then, and this is something that's only come up in say, the past few years, is that these celestial bodies, these galaxies, they're not slowing down. In fact, they're accelerating away from each other. Coming back to the rock example, this rock, as soon as you let go of the rock, it starts to slow down. Its velocity reaches zero right at the peak of its path, and then it starts coming back down again. And so, just to give you an idea of how weird this is, that the galaxies are not slowing down and that the Big Bang is actually accelerating, imagine taking this rock, throwing it in the air, and then the rock just starts speeding away from you, out into space. That's how weird this is, that the galaxies are accelerating away from each other. Again, if you saw this happening, it would be very strange. And so the hypothesis that's been presented to sort of explain why these galaxies are accelerating away from each other, is that there's something called dark energy. And this dark energy is what's pushing the universe apart. And so this dark energy is essentially counteracting gravity in such a way that that the Big Bang is continuing, and we're never going to get into a big crunch. And at some point, every galaxy will be so far away from every other galaxy that you'll be able to look up in a telescope. You'll be able to look in through a telescope and you won't see anything. You won't see any other galaxies because they've been pushed so far away. What is the dark energy? Nobody really knows. That's why it's called dark. You can't see it. We don't know where it comes from. All we know is that something is pushing the universe apart. And so that's been called dark energy. All right, thank you.